Flipped classroom video for Maths A2 Unit 3, Differentiation of Implicit Functions. So, implicit differentiation. What's the essential point? Well, if we look at an example of an implicit equation, we can draw out the problem that we have with them. To use the techniques of differentiation that we know about, or that we have at our disposal so far, we'd like to be able to convert this into y is a function of x. But unfortunately, we don't have any algebraic techniques for this. There are techniques, and they would give us this function here. Now, that is insanely complicated, and you're welcome to have a go, but I do ask the question, does anybody fancy having a go at differentiating this using the rules that we have? We can see that we've got powers of a half, so those are the square roots. We've got cube roots, we know how to differentiate them. We've got products and we've got quotients, and we know how to differentiate them. So theoretically we could differentiate this, but do we want to? So there must be a better way, and thankfully there is. So essentially we're wanting to differentiate functions of y with respect to x. So dy by dx is y differentiated with respect to x. So the problem we have is we've got functions of y involved in our implicit equation. So we need to be able to do d by dx of a function of y, not just of y itself. And to do this, we apply the chain rule, and that does allow us to differentiate f of y with respect to y. So we've got d by dx of f of y, but by the chain rule we can replace d by dx by dy by dx times d by dy, and then we have our f of y there. Now, differentiating f of y with respect to y is just ordinary differentiation. So we have sort of solved the problem. Let's have a look at an example. So if we needed to differentiate y to the power of 4 with respect to x, then that's going to be dy by dx times d by dy of y to the 4. Now we know that when we differentiate y to the 4, we're going to get 4y cubed. So we end up with dy by dx times 4y cubed. So, in brief, for functions of y, we differentiate them with respect to y and then multiply what we get by dy by dx. We can apply this idea bit by bit to the equation that we've already met. We want to differentiate with respect to x, so we'll start with x cubed, so d by dx of x cubed is 3x squared. That's quite straightforward and familiar. Now we need to differentiate x squared y. So this is a product of functions. We've got x squared times y. So we differentiate the first function, x squared differentiates to 2x, and we times that by the second function, which is y. And then we keep the first function, x squared, and we differentiate the second function. So we're going to differentiate y with respect to x, and in fact, and this is a really important point, this is the familiar dy by dx. So we end up with 2xy plus x squared times dy by dx. Okay, we now need to differentiate y to the 4, which we've already done. So d by dx of y to the power 4 is dy by dx times 4y cubed. And we also need to differentiate 17. So differentiating a constant always gives us 0. And then we can put all these things together. So we had x cubed plus x squared y plus y to the 4 equals 17. When we differentiate, the x cubed becomes 3x squared. So then we add on the differentiated x squared y, which gives us 2xy plus x squared dy by dx. Then we add on the differentiated y to the power of 4, which gives us 4y cubed dy by dx, and that will then equal the 17 differentiated, which is 0. And we've got some of the way there, but we haven't finished yet, because that's not telling us what dy by dx is, which is what we want to know. So, finishing off, this is just the previous line repeated. So what we need to do is gather all the terms that have dy by dx in on the left hand side. Then we take, or at the same time generally, we take the dy by dx out as a factor, and then the other terms we need to put on the right hand side. So how does that work? Well, on the left hand side we have an x squared times dy by dx, and we have 4y cubed times dy by dx. So we can take dy by dx out as a factor, which gives us x squared plus 4y cubed all times dy by dx. On the other side, we need to subtract 3x squared and subtract 2xy so that we don't have it with our dy by dx bits. So that gives us equals minus 3x squared plus 2xy. Notice we've bracketed them and put the minus on the outside for neatness. And now, in order to find out what dy by dx actually is, we just have to divide through by that bracket that's multiplying it. So we divide through to get dy by dx is minus 3x squared plus 2xy divided by x squared plus 4y cubed. So, very complicated, but we've got there. Let's try another one as well from a previous video. This time we'll do it directly rather than splitting it into bits. So, if we want to differentiate x to the power of 4, then that's going to be 4x cubed. To differentiate sine y, well, we have to differentiate that with respect to y and times by dy by dx. So sine y differentiated with respect to y is going to be cos y, and then we're going to times it by dy by dx. For the final bit on the left hand side, we've got to do the product rule. So first we differentiate x squared, which gives us 2x times the y cubed, and then we keep the x squared and we differentiate y cubed. That means differentiating y cubed with respect to y, which gives us our 3y squared, and then timesing by dy by dx. On the right hand side, of course, we just have a 9, and when we differentiate that it becomes 0, so that line finishes with equals 0. Next step, we're going to gather our dy by dx terms and take dy by dx out as a factor. So we've got cos y times dy by dx, and we've got x squared times 3y squared, which we can tidy up to say 3x squared y squared. So we've got numbers, then x's, then y's. And that's all going to be times by dy by dx. And then we're going to be subtracting the 4x cubed and the 2xy cubed. So that gives us equals minus 4x cubed plus 2xy cubed. Finally, we have to divide by cos y plus 3x squared y squared. So we are left with, in the end, minus 4x cubed plus 2xy cubed over cos y plus 3x squared y squared. Okay, so we'll look at an applied example, if you like, finding the tangent or normal to an implicit curve. And the example we're going to use is finding the equation of the tangent at the point 3, 1 for the implicit equation x squared y minus 2x plus 3y cubed equals 6. So, the first step is to find what dy by dx is. So, working our way through, x squared y is a product, so we have to first differentiate the x squared to get 2x times the other function, which is y. Then we keep the x squared and we differentiate y, which is just dy by dx. The minus 2x is going to differentiate to minus 2, and then 3y cubed, well, we'll differentiate with respect to y, and that's going to give us 3y squared times the 3 we've got, so that's 9y squared, and then we have to times by dy by dx by the chain rule. On the other side, we've got equals 6, which becomes equals 0 when we differentiate. Then we gather our dy by dx terms, so we've got x squared plus 9y squared times dy by dx, and we subtract the other terms, so they become 2, take away 2xy on the other side. The minus 2 we're adding, or we're subtracting minus 2, which is the same as adding 2, so that becomes 2, and the 2xy we're subtracting from the left hand side, so we have to subtract it from the right hand side. Okay, and finally, you will be fed up of hearing this, but we divide by whatever's multiplying dy by dx, which gives us our final form for dy by dx, which is 2 minus 2xy divided by the x squared plus 9y squared. Okay, so we now know how to find the gradient, which we need for the tangent, of course, and so we can move on to step 2, which is finding what dy by dx is at the point that we're interested in. And so now, having seen in the last few minutes how to differentiate an implicit function, we're now going to see how to find the value at a particular point. And so dy by dx when we're at the point 3, 1 is equal to, and what we have to do is simply substitute our values for x and y into the equation we have for dy by dx. So on the top we've got 2 take away 2 times x times y. So I've for some reason written that slightly oddly because I've put 2 take away 2 times y times x, but never mind. You can see that the 2 times 1 times 3 is 2 times the y value times the x value, which is what it says on the line above. On the bottom of this fraction we start with x squared, which becomes 3 squared, and then we have plus 9y squared, which is plus 9 times 1 squared, which is of course just 1. Okay, if we tidy that up, we have 2 take away 6, that's the 2 times 1 times 3 on the top, and we have a 3 squared plus 9, which is 9 plus 9. That gives us minus 4 over 18, which gives us minus 2 over 9. And we best keep it as a fraction because then we'll get a nice form for the equation of the tangent when we get there. Okay, step 3, find the equation of the tangent. Okay, so we're going to use the easiest way of doing this. We know a point on the line of the tangent, which is the point 3, 1. We know the gradient of the tangent, which is our m in this y minus y1 equals mx minus x1 form, and so we can just plonk them in. So y minus y1 is going to be y minus 1. M is replaced by our minus 2 over 9 that we've just calculated, and then in the bracket we have x minus 3, which is the x coordinate of the point we're dealing with. And we can tidy that up into a y equals mx plus c form. I'll let you faff about with the arithmetic, but we end up with minus 2x over 9 plus 5 over 3. And we can, if we like, make that into a standard form which is rather neater. So by timesing through by 9 we get, and rearranging, we get 2x plus 9y is equal to 15. And we can have a look at a little picture of that because it's nice. And the red curve, that's our implicit curve, and then we can see the tangent at 3, 1.